So take it away, Dr. Lee.
I can. I cannot share screen. Okay. It's you disable the participant screen sharing, so maybe you have to.
I think you should be able to do this now.
Okay. Let me see. Wow, which one? Is the right one I'm sharing? Okay.
Yes, it looks good.
That's not good. Okay, so thank you for giving me this opportunity to present the laser nuclear spin polarization facility at TRIUMF, also talk about its application. Okay, so first thing I will tell you where we are. We are at the city of Vancouver, west coast of Canada. So here is a photo of the Vancouver downtown. So you will see the beautiful Pacific Ocean. Also, there's a very beautiful Stanley Park nearby the downtown. UBC is at another side. Here is the UBC campus. TRIUMF is at the south campus of the UBC. TRIUMF was founded in 1968 by 3 universities. So that's why it's called the Tri-University Maison Facility, TRIUMF. TRIUMF has the world's largest cyclotron, which provide up to 520 MeV. The diameter of this cyclotron is 18 meters. So it's the biggest diameter cyclotron in the world. After 50 years of expansion and development, TRIUMF nowadays have 20 Canadian university members, and we're working with 50 foreign institutions in 30 different countries. Inside TRIUMF, we have 350 scientists, engineers, technicians, also 150 postdoc fellows, graduate students, and co-op students. So the cyclotron provide a high energy proton beam. So we can use this proton beam in different ways. One of the ways to use a proton beam is to generate a radioactive isotope. So we have this big facility. It's called ISAC. It's the name for the isotope separator accelerator. It's used to generate radioactive isotope to study nuclear physics, astrophysics, material science, also life science. So how we generate those radioactive isotopes? We hit the high energy proton beam on the target. The target is made of heavy element material, such as uranium, tantalum. So the proton hit the bigger nucleus of those heavy elements and break the nucleus to the small pieces. So then we generate a lot of radioactive isotopes of the lighter elements. So those radioactive isotopes will extracted and accelerated by the electric field generated by the high voltage potential, and it will accelerate the ion to as a fast ion beam. Those fast ion beam will send to the different experimental stations, so we can perform different scientific research before it's decayed. So the polarizer is located in the low energy benign areas here. So this is the layout of the polarizer. So the low energy radioactive beam enter the polarizer in the one side, and the laser beam enter the polarizer from the other side. So the ion beam and the laser beam interact with each other inside this polarizer. The laser beam will polarize the ion beam, and the polarized ion beam will be bended and sent to the different experimental station. So here we'll see the BetaMR, 2 BetaMR station, also one beam line to Osaka station. Osaka is used for the nuclear physics studying, BetaMR measuring for the material science studying. So the initial motivation of build this polarizer in 2000 is to provide the hyperpolarized radioactive beam to the BetaMR study. So we use this method called collinear optical pumping to provide the polarization up to 90%. The typical nuclear polarized beam we provide is lithium 8, magnesium 31. So since we have the major application of this polarization facility is for the BetaMR. So here I will give a brief introduction about why people favor BetaMR. So most people know the NMR, nuclear magnetic resonance. So it's a very powerful tool to study material science, biochemistry, and the nuclear physics. However, the conventional NMR has a small degree of polarization, also the low detection efficiency. Compared to the conventional NMR, BetaMR can use a laser to generate up to 90%. In theory, we can reach 100%. This is super polarization. Also, the detection method of BetaMR are different. So because of beta decay actually have the favor the emission direction related to the nuclear spin. So use this asymmetry of the emission direction, so we can measure the rotation or change of the nuclear spin. So this detection method is direct detection of the charged particles. So it's a very efficient detection method. So combine this two increase of the sensitivity. So BetaMR compared to the conventional NMR, normally have a more than 10 order magnitude more sensitivity. Also, there's another advantage of BetaMR is that since we use the fast beam, so we can change the energy of the ion beam, so we can specifically depose the radioactive isotope in the depths we want. So this spatial resolution we can reach into the scale of the nanometer. So that's why BetaMR very often used for studying the nanostructures and the new materials such as the quantum materials. Also, it can used to study the interface of the two materials. It is very useful for the semiconductor industry. However, the BetaMR is not very popular in the world. That's because it have to use the short-lived radioactive beams. So only the several facilities in the world can provide this access. Ultron is one of them. So how do we use the lasers to polarize the nuclear spin? So when the laser interact with the ion beam or atomic beam, it actually excites the atomic states. So it's manipulate atomic states. But how we can, when we manipulate this atomic state, we can change the nuclear states. So if you think about the angular momentum of the atom, it's a total angular momentum of the atom. It's the result of coupling the nuclear spin angular momentum and the electron total angular momentum. So that means if we excite the atom state to some specific magnetic sub levels, so we actually also excite the nucleus to the some specific magnetic sub level. So these two states are associated with each other. So that's how we just by manipulate atomic states, we can also control the nuclear states. So this is how we do exactly on the lithium 8 as example. So lithium is a very popular beam we polarize in our facility. Lithium is quite simple, have a quite simple electronic structure. It have a one valence electron. So it have this transition from the ground state to excited states. Wavelength is 671. It's a closed transition. so without leakage. So it's a very good good structure to do the optic pumping. But we have to pay attention that there's some height splitting at the ground state. That means we have to use 2 laser beam to do this optic pumping. Otherwise, we will lose the population. So here shows how it do. So we use the circular polarized laser to interact with the missing atom. So because of the polarization of the income laser beam, so the selection rule of the possible transition is limited to the delta J equal to 1. So that means that all the atomic state population will be pumped through the one direction from in this diagram from left to the right. So after several cycles, which means pump up and then emit down, after several cycles of this optical pumping, the most population will accumulate in this states. And this state is a dark state because there's no other way to go out. So this state is it's the 5½ MF equal to 5 half states. It will associate with the nucleus spin states MI equal to 2. So in this case, we also polarize the nucleus spin. So this is how the configuration of the polarizing atom look like. So in our facility, we can polarize ions, also can polarize atoms. So this is just an example to show how we polarize the atoms. So the lithium 8 beam, ion beam come in. So because the laser only interact with this wavelength laser only interact with the neutral lithium, so we have to neutralize first. So we use this rubidium vapor cell to neutralize the lithium, and then the neutralized lithium will interact with the laser and do the optic pumping through this 1.9 meter region. And some of the ions will not neutralize. Then we use this ion deflector to bend it and dump into this Faraday cup. After the lithium be polarized, it will enter this helium cell to be reionized. After it reionized, we can use the electrostatic bender to bend it out away from the laser beam, so we can send it to different experimental station. So this is how the real thing look like. The laser go this way, the ion beam go this way. So the rubidium cell is here, the helium cell is here. So it's a neutralization and the reionization. In between, it's the optic pumping region. So this is how the laser setup look like. So we use the ND-YAG laser 532 nanometer laser to pump the dye laser. Dye laser is a typical coherent 8 light line. The dye laser provides 673 nanometer laser. The power can reach 280 milliwatt. So this dye laser will go through three electro-optical modulator. Later on, I will talk about why we need to do this, and then send it up to the ISAC hole and enter the polarizer. Before it enter the polarizer, we have this 2 wave plate to manipulate the polarization of the laser. So we have some pickup of the lights from the dye laser. So one of the part is sent to the wavelength meter to monitor the wavelength of the dye laser. Another part we send it to this interferometer. We also have a reference stabilizer helium neon laser. This will also send into this interferometer. So both lasers will generate interference pattern from this interferometer. So we can use the computer to analyze those fringes. So we can lock the dye laser to this stabilizer helium laser. I will talk about this later too. Okay, this is how the laser table look like. This is a dye laser, pump laser, EOMs. Also, these 2 interferometers. This one is for the locking laser. this one is for to absorb the effect of the EOM. Here is the Yin-Yang reference laser. So why do we need to use those three EOM? So those two functions. So one is to pump both hyperfine ground states. I mentioned before there's two hyperfine ground states for lithium. So we only have one laser. So how we can pump both ground states? So we use the EOM to do it. So the laser enter the EOM, when it go out, it will generate the 300 megahertz frequency sideband. So then this frequency difference exactly match with the splitting of the hyperfine splitting of the ground states. So then we can use these two laser component to at the same time to excite from both hyperfine ground states. So there's another two EOMs, 19 megahertz and the 28 megahertz EOM. Those are used to broaden the bandwidth of a laser to match with the absorption profile language of the beam. So typically it's 100 megahertz we have to match with. So this will show how to do it. So at the beginning, it's a single mode laser, and then we generate the sideband, then we generate more sideband. So eventually it's generate about 100 megahertz envelope of this bandwidth laser. So we can exactly match with the language of absorption profile. So we also, as I mentioned before, so we use the interferometer to do the frequency locking. So the Yin-Yang laser and the dilaser enter the interferometer, generate this fringing. So we send this image to the computer. The computer will calculate the separation of these two fringing from Yin-Yang laser and the dilaser. So the computer will try to calculate this every 1 second. You can change this. Depends on how good it is, which one provide better locking. So then then you send the, well, if this distance changed, you can send the feedback to the dilaser to correct it. So then this way we can actively lock in the dilaser wavelength to the stabilizer Yin-Yang laser. The interferometer is a temperature stabilized to 0.1 degree. The major cause of a laser drift is air pressure variation. The long-term dilaser frequency stability is about 5 megahertz. So since it's the first commission, sorry, did something happen? Hello?
Yeah, I think your PowerPoint stopped.
Huh? Oh, yeah, right.
We only see your screen.
That's strange. Why it stopped? Okay, so sorry. Yeah, I don't know what happened. Okay, since its first commission in 2000, the Polarizer has been routinely provided the lithium 8, lithium 9, and magnesium 31 to the BetaMR station for the study of material science and the molecular science. But it also provided beam to the life science, nuclear science, and the fundamental symmetry. So we are right now want to expand the application of the polarizer. So we have to develop more new nuclear polarized beams. For example, as a life science, as an example, so in the recent years, there's a high interest to use the nuclear polarized magnesium, also copper beams, to studying their behavior inside the biophysics system. So those elements is essential metal ions inside the human body. For example, for the copper, some people believe and the copper accumulation inside the human body actually it's related to the Alzheimer disease. Also, there's some interesting to require the nuclear polarized actinium. Actinium is one of the isotope who doesn't have stable isotope, so it's a chemical properties is really not well known. But actinium 225 is a very promising candidate for the cancer treatment also. So this is highly motivated people to want to get know better about this element, especially its behavior inside the biophysics environments. So to meet all the needs coming from the different research group, so we want to do more developed work on the polarizing radioactive isotope. But there's some difficulty to doing this. So firstly, different isotope have a different isotope shift and the hyperfine structures. That means for each isotope, we have to do the individual development work. And so we have to know the hyperfine structures, so we can set up the proper laser system to do it. So also when we extend the isotope element from the methane like alkali element to the like a copper more complicated elements, we have to have to reach those difficult wavelengths such as blue and the UV wavelengths. So we need to do the frequency doubling. For the CW laser, which normally means we have to do the cavity and the cavity knocking. So it's quite complicated. Also, it's a very sensitive systems for the delivery properties of our facility, which need a really long-term stability, and it's not a good way to do it. Also, because for the methane, I showed you it's a closed transition we are used for the optic pumping, but for the copper and the magnesium is okay. For the copper and the zinc, in the future development work, so we need multiple lasers to repump the population from metal stable states. That means if we start excited from the atom state, from ground state to the excited states, it's not always go back to the ground states. It also can leak to some metal stable states. After several optical pumping, the accumulation of the population on those states will become bigger and bigger. So then we lose a lot of population. Then our polarization efficiency will not cannot reach high. So for some required isotope, for example, copper 58, copper 74, also actinium 230, 232. And those isotopes, it's a short-lived isotope. It's rarely studied, so their hyperfine structure are not known. So this means we have to do some studying before we really do the laser polarization. But from the bright side, if we look at it, so there's some byproduct from those development work. So we can measure the unknown hyperfine structures, also the isotope shift of those exotic isotopes, such as 230, 232 actinium, from which we can extract some nuclear properties. So such as mean square charging gradient, and the nuclear spin, nuclear dipole moment, nuclear quadrupole moment. So from those nuclear parameters, we can know the shape and the size of the nuclei. So here I show this complicated optical pumping scheme of copper and actinium. So you see this for those metastable states, also for the excited states of actinium, we don't know the hyperfine structure, so we have to do this spectroscopy before we really do the laser polarization. So this will be the major development work in the coming couple of years for our facility. So, so are we gonna always stick to this complicated development path, or we can find some universal method in the future to do this, to do the laser polarization? So there's some ideas. So first one is it's to use the pulse laser. The pulse laser have some advantage. The first thing, it's broadband, so it can cover the all the Hi-Fi structures in most of the case, and so then you don't need to load the details of the splitting of the structure. You can just pump it and then often pump it up. And also it have a very high power. And so especially for the frequency doubling, frequency tripling process, which are nonlinear process, the efficiency of those conversion ratio is highly related to the power. So when we use a pulse laser, it will be much simpler than the CW laser do the frequency doubling. We can just a single pass through the nonlinear crystal. We can achieve the quite good power out. And so that's will much easier for us to access the blue and the UV wavelength region. But there are also some problem with this pulse lasers. So because it's really short duration, so this short interaction time with the atom and ion beam, so normally in the time scale of the nanoseconds and tens of nanoseconds, it's too short to allow the multiple optical pumping cycle to really populate the substates we want. So there's one solution is proposed by this paper. So it's to use the optic cavity. So we put a cavity, we build a cavity with the laser. So the laser part will reflect back force within this cavity. So then, because the speed of light is much faster than the speed of the ion beam, so then when the laser powder return back, it still illuminate the ions in flying. So so in this way, in the total effect will like the laser powder extract inside this cavity, so it will significantly increase the interaction time. So we hope we use this method, we can achieve the laser polarization on the nuclear radioactive isotopes. Use a powerful pulse laser. So another way approach is use the alkali vapor spin exchange cell. So it's similar to the rubidium cell I talked about at the beginning when we do the lithium neutralization. But in this case, we put a laser inside this cell. So the laser will polarize the rubidium inside the cell. So and when the ion beam enter the rubidium cell, and the rubidium vapor will transfer its electron, which is polarized already, to the ion incoming ions. So then this ion will take this polarized electron and then become neutral atoms, but it carried that angular momentum, then it polarized the two. This one, so we have some people actually at TRIUMF. He did this pioneer work on this technology like in 1990. So we have some build up knowledge on to build this cell. This is the advantage of this project, but we also have to think about a lot of problems. For example, the radiation trapping will cause depolarization in the dense vapor, like the rubidium cell. That means that when the rubidium absorb some speaks of polarization photons, and it will emit out, but when it emit out the photons, it's random polarization. So in the very, it's not in the not density vapor condition, those fluorescents will come out, will escape very quickly. So it will not interact with the second atom, but in the dense vapor condition, like this rubidium cell, so it may reabsorbed by another rubidium atom. So then it will depolarize that atom. So the possible solution is we mix the two alkali species. So then it will lower the density of the rubidium cell. Also, we have to think about the depolarization on the cell wall. So that's also maybe can do some wall coating too. So all those is still in the proposal phase. So we want to apply some fundings. Also, some students come to studying in this project in the future. So this is the end of my talk. Thank you very much for attention. So if you have some questions or comments, please bring it up. So I also welcome the students to discuss with us about our research, also the future opportunity to join our group. So please contact me via this email address. Thank you very much.
So we have time for questions.
Yeah, okay, I have a question.
Okay.
I have a couple of questions, actually. I was quite interested to see that you're using lithium-8 and lithium-9. I was involved with determining the nuclear charge radius of these from the isotope shift.
Oh.
And yeah, so I'm Gordon Drake from, so I was part of the theoretical interpretation of the measurements for these. And I noticed you're also planning on using the isotope shift for some of these heavier atoms. Is there someone providing theoretical support for that? Because you need to have a description of the atomic structure part of the problem in order to calculate the isotope shift. So is there someone working on that, on the theoretical part?
Not a lot of, so
yeah. So how do you get the nuclear charge radius from the isotope shift? How do you make that connection?
Yeah, we have some. I'm not really doing the collinear laser spectroscopy. So Matt Pearson in TRIUMF, he is doing those things. So they collaborate with some nuclear physicists. They do the calculation about those things. So I'm not really know the details of how to do it. I only know the basic things. They are connected. Yeah.
Okay. Can I ask another question?
Sure.
Yeah, on slide 18, you said the short interaction time. Let me show that. Yeah, you said it's limited by the short interaction time. Is it so short just because the beam energy is high? It looks like you have 20 keVi on beam.
Exactly. So it depends on the speed of the beam. Yeah, you can make this interaction longer by making the velocity lower. But
Yeah.
this is it's not a big amount of the change. Also because the laser part, so the laser pulse, the typically used laser pulse is a nanosecond range.
So have you looked into methods to slow down the beam to increase the interaction time?
So
Yeah, can you slow the beam down?
I can slow the beam down to some energy, but I cannot totally slow the beam down because also for the BetaMR, for other, so they need the energy, the beam have a certain energy, so they can do the implantation.
And of course, you might get a spread in it, a larger spread in energy if
You
you do.
also, yeah,
Yeah, if
so
you slow
it's
it down, you also lose energy
yeah.
resolution. Then,
So
yeah.
all the ion optics maybe have to change. Yeah, so it's designed for the 10 keV to the 30 keV at the beginning. Yeah.
It's quite a long, a 2 meter optical interaction region. It's quite a long
Yeah,
interaction region.
for the lithium 8, typically it's take about shorter than 10 microseconds to travel through this region. Yeah. So for example, if we use the 671 nanometer transition, which is like when you pump it up and decay down, it takes like 30 nanoseconds, or its lifetime of the up states is short. So it's very efficient. You can do this multiple cycling. Yeah. So but for some transitions, if it's weaker, so it's more difficult. For example, when we think about repumping the copper, the metastable state transition, this one, it's much weaker. So when we do the repumping, it might cause some problems. So yeah.
Right. Okay, well, I'll give somebody else an opportunity to ask questions.
Sure. Thank you. Yes, regarding to your question about this nuclear properties, certainly we don't doing this, but we will collaborate with Matt Pearson when doing this collinear laser spectroscopy about this HAP5 structures. So then we can collaborate with some international nuclear physicists, or we can collaborate with you, so we can think about how to calculate those.
Yeah, I'm afraid the sound quality isn't very good. It's hard to pick up everything you're saying.
Oh, sorry.
Just so I understand how this works, when you're talking about the sensitivity on slide 5, um, you're going down to 10 to the 6 atoms. Yeah. So just so I understand how this works, the idea is to implant the ions into some material. Is that the way it works?
Yes. Yeah.
And so what is the lifetime of, let's say, lithium 8? How long do you have to work with it?
It's 803, it's 38 millisecond. It's 800 millisecond around. Yeah.
800 milliseconds, do you say?
Yeah.
Well, okay, so you have to be pretty quick. Yeah, you can't wait around. You can't go for a cup of coffee and then come back and do the experiment.
Yeah, but we keep just implanting, right? So yeah.
Okay, very good, very interesting talk. Thank you.
Thanks.
It's good to hear what's going on in TRIUMF.
Yeah, Ruohong, I had a question as well, which I think you just answered, but I wasn't exactly sure if I had caught it all. So are all of these experiments on the hyperpolarized nuclei, they are all done on the beam, meaning that they're directed afterwards and done there at TRIUMF? And are any of these nuclei taken out of the beam and held for use off site, or are all the experiments with the nuclei that you polarize done there at TRIUMF because they're so short-lived?
Yeah, it's so short-lived. We just use on the station. We cannot, transport outside.
Okay. Yeah. I thought so, but I just thought I would ask. It was clear after you answered Dr. Drake, but I wasn't sure about that beforehand. So too bad. I think, yeah.
Okay, so if there are no other questions, let's thank Dr. Lee again for a really interesting talk.
Yes,
and
thank
thank
you.
all of you who have been coming every week to this undergraduate seminar series. Especially, I think Dennis and Carolina Benares, I've been seeing you every week, and that's really enjoyable, that it's really meant for people to come to. So I hope everybody continues to come. We're planning on continuing the series, and we'll keep you posted if that happens. And thanks to all the speakers in this series again.
Oh, I guess I see Aaron Bondi joined. A message just came out. So I guess some of my students came in.